Good morning, class. We are looking at statistic practice test number 5, module 5, covering chapters 10, 11, 12. Chapter 10, correlation and regression. Chapter 11, goodness of fit and contingency tables. Chapter 12, analysis of variance. So here's chapter 10, correlation and regression. Number one, given the sample data. As you can see, it's a very small sample data. Find the value of the linear correlation coefficient, or test the claim that there is a linear correlation between the two variables x and y. Use both A method 1 and B method 2, alpha equals 0.05. Find the regression equation. Find the best predicted value of y when x is equal to 2. There's a lot of information here. So let's look at each case and the concept first. By the way, again, from here on, mostly technology is used. I chose a very small sample to show you how it's done by hand if need be. So first and foremost, what are we dealing with here? Scatter plot and the strength of the linear correlation, R represents the linear correlation. A scatter plot is a graph of the ordered pairs x and y. X, as always, the independent variable, y, the dependent variable. So you plot the points. There are many points, as you can see here. And you try to draw a line, if possible, in this case with a positive slope. It's a distinct straight line or linear pattern. We say that there is a positive linear correlation between x and y, since as the x value increases, the corresponding y value also increases. If there is a strong positive linear relationship between the variables, the value of R will be close to 1, positive 1. So such as 0.7 or large. Take a look at this one, positive linear correlation. What happens here? Again, bunch of points. You plot those pairs. There seems to be a correlation, distinct straight line or linear pattern. We say that there is a negative linear correlation between x and y, since as the x values increase, the corresponding y values decrease. If there is a strong negative linear relationship between variables, the value of R will be close to -1, meaning -0.7 or smaller. So R is only between -1 and 1. Don't mix it up with the probability, which is between 0 and 1. What happens here? It's all over the map, the pairs. There is no correlation, no distinct pattern, which suggests that there is no correlation between x and y. So if you look at this line, correlation value R is somewhere between -1 and positive. From like 0.7 to +1, strong positive linear relationship. From -0.7 to -1, strong negative linear relationship. In between, no correlation, especially the closer it gets to the value of 0. Now, correlation does not imply causality, meaning just because two things happen at the same time or seem related doesn't mean that one causes the other. And R is always between -1 and 1 inclusively. That means they include the two numbers. A simple example, this is a classic example that is used. to indicate the concept of correlation versus causality. Ice cream sales and drowning incidents both increase in summer. Correlation. These two trends go up together, but not causation. There is no causation. Ice cream does not cause drowning. Instead, a third factor, hot weather, leads to both. So that's the concept that we are looking at. Now let's actually work on the question that was given in the first place. So we are given the data, and here's the formula, everybody. R is n summation of xy minus summation of x times summation of y over the square root of brackets n summation of x squared minus summation of x quantity squared, close brackets, open brackets, n summation of y squared minus summation of y in the parentheses squared. It's a very interesting and sort of complicated formula. I want to show you how that works in case by hand. Again, nobody would expect you to do this by hand, but this is small enough. We have only 4 pieces. Obviously, n is 4. That's the first thing. 4 pairs. So as we look at this, we need to come up with x. So we write the x here. We write the y. We want x times y. We need it, right? X times y. We need x squared. We need y squared. So let's do that. For example, x times y. So how do we get that? 1 times 2 goes here, 2. 1 times 8 goes here. 3 times 6, 18. 5 times 4, 20 goes here. X squared. X squared. Let's square the first column. 1, 1, 3 becomes 9, 5 becomes 25. Let's square y. 2 becomes 4, 8 becomes 64, 6 becomes 36, 4 becomes 60. So that's x times y. That's x squared. That's y squared. Very straightforward. Calculation is very easy. It's a little bit tedious and long, but the concept is understood. Now, we need to add them up because, as you can see, with all those summation signs. So let's add them up. This becomes summation of x. For example, 1 plus 1, 2 plus 3, 5 plus 5 is 10. And we do the same thing for each column. Summation of x is 10. Summation of y is 20. Summation of xy is 48. Summation of x squared 36. Summation of y squared is 120. And now we can put it into a calculator. 4 into the formula. 4 times 48, right? N is 4 times summation of xy. That's the formula we are going to use. That's the formula, everybody. Okay. 4 times 48 minus summation of x, which is 10, times summation of y, which is 20. That's the numerator. Then square root. Inside this square root, we start with the n, 4, summation of x squared, 36, minus summation of x, which is 10, quantity squared. So that's the first bracket. Second bracket, we do the same thing with the y. N summation of y squared, which is 120, minus summation of y, which is 20 squared. You put it into a calculator. Minus 8 over the square root of 44 times 80, and you end up with negative 0.135. Again, the sample is very small. It can easily be done by hand. Okay, and that's the idea. If you want to use a calculator, for example, to our calculator, we first put in into L1 and L2. This is L1, this is L2. So first you clear the list. stat, edit, clear the list. Then you put it into L1 and L2. So in L1 goes the X values 1135, and in L2 goes the Y values 2864. And now we do linear regression t-test. Linear regression t-test. It does a lot of things. For now, we are concerned with the value of R. So for the X list, obviously L1, Y list is L2. This you can ignore it. And this one is for the you put not equal to, and you do the calculation. That's for the test of hypothesis. And so this is the linear regression test and the linear regression equation. Again, we're going to ignore it for now. We're going to come back to this as we continue with this question. But for now, we are interested in the value of R. Take a look at this one. Take a look at this one. If you stop at 4, next to it is 8, you change it to 5. Of course, it depends on how many decimals they ask you. So you don't have to do this by hand. You can do it by using any technology, but I'm showing you step by step how you arrive at it if you want to calculate it by hand, or at least we have an understanding of that. And there are other technologies you use. I have given you many calculators on. All right. Now we want to do the test of hypothesis. So test the claim that there is a linear correlation between the two variables x and y. Use both methods. Whether the two methods, I want to discuss that in a moment, and reminding you from the previous page, n was 4, r was calculated to be negative 0.135. This is from the previous page. So as you recall, we have 4 pieces: null and alternative hypothesis, test statistic, distribution from the critical value, make a decision. All of those, we are going to do the same thing. So the first part, the null and alternative hypothesis is the same. H0, rho equals 0. Rho is the Greek letter, remember, for the test of hypothesis, you always use the population parameter, and for correlation is rho. Rho equals 0. Always. Equality goes for H0. H1, rho is not equal to 0, which makes it the two-tailed test, which makes it the claim. I want to explain this one. First of all, rho is not equal to 0. That means that there is a correlation. Rho equals 0, that means there is no correlation. Okay, so this means no correlation. This means there is a correlation. So we always have these two. This makes it a two-tailed test. It's always really a two-tailed test. I mean, even if you use a left-tailed test, it results in the same thing in the process. And this is the claim. The claim is there is a correlation. Okay, so you're testing the correlation. So what are the methods? Method 1, we have to calculate the test statistic. In the first method, we use the t-distribution, and therefore the formula is r minus mu sub r square root of 1 minus over square root of 1 minus r squared over n minus 2. That, by the way, mu sub r or rho equals 0. This is the same thing, again, depending on the text that you're using, and this is always coming from H0, and therefore it's always 0. The other formula I want to mention is this. I hope you see these two are the same. Okay. First of all, mu sub r is 0, so ignore that. This part, if you put it next to r, you can flip over this one. So these two formulas are identical, with the exception that we are taking this to be always 0. And degrees of freedom, because you have two variables, is n minus 2. So you plug in what is R. R has been calculated here as negative 0.135. And then you just put it into a calculator. Okay. So negative 0.135 minus 0 is square root of 1 minus negative 0.135 quantity squared over 4 minus 2. And that results in negative 0.1927. So that's the test statistic if I want to use the basic t-test. The second method just uses the value of R as the test statistic because it uses a different table. We're going to discuss that in a moment. What about here? We are using the t-test, and as always, we choose alpha. Normally, alpha is 0.05, otherwise it's mentioned. So alpha is 0.05, degrees of freedom is n minus 2, and that makes it 4 minus 2 equals 2. From the table, we get two values, plus minus 4.303. This is the good old t-test, the t-table. The second method here, how do we get the test statistic? N is 4, alpha is 0.05. We use R, critical value, from Pearson correlation coefficient table. I will show you the table in a moment. From the table, we read those two values. So, to make a decision, what do we do? To make a decision, for the t, we draw a normal curve. We have the two critical values of plus minus 4.303 and the test statistic of negative 0.1927. I hope you can see that it's in between. I'm going to show you in a moment. This one, for this one, you draw a line. And it goes from negative 0.95 to positive 0.95. And R, which is negative 0.135, is somewhere in between. So take a look at this one. This is for the first test. T is plus minus 4.303, so negative, positive. Your test statistic is what? Way into the non-rejection region. Fail to reject, rho is 0 there. Okay, fail to reject, rho is 0. The method 2, okay, so rho is equal to 0. The second method uses just a number line in essence. We put, remember, correlation goes from -1 to +1, okay? That's why in essence from -1 to +1. You have negative 0.95 here, positive 0.95 here, and this number belongs somewhere. It belongs in between, way inside the non-rejection region. Fail to reject H0. So if you're not rejecting H0, what are you rejecting? H1. So the claim becomes false. What does it mean? There is no linear correlation between the two variables. That's what it means. Now, as far as the technology, I showed you in the previous page how we do the linear regression t-test. What do we find there? There are a couple of numbers I want you to notice. This is one of them. We calculated the test statistic here by hand. Here's the technology version. Minus 0.19245. It's slightly different again. Remember, technology uses a lot of, right here, for example, this number is not used. It's used with a lot of decimals. Okay. What else do we notice here? This is the p-value, larger than alpha 0.05. So it's 0.865, let's say with 3 decimals. When the p-value is larger than alpha, fail, okay? Do not reject or fail to reject H0. We get to the same decision. Now, what I want to show you is this. If you go with method 1, the t-test, and in both cases, alpha is 0.05. Degrees of freedom is n minus 2 equals to, that means this point. Area in 2/3 is this one, 0.05. The answer is 4.303, and we remember we said the critical value was the same thing, plus minus. So plus minus 4.303. Now this, and you have it in your formula sheet, is called Pearson correlation coefficient R. We know n is 4, so you look for n equals 4. You know alpha equals 0.05, you choose the alpha. So it comes together here, the answer is 0.950. Because it's a two-tailed test, it's plus minus 0.950. This is how you read the two tables. Again, this you had seen, and this is sort of new. Now, continuing with this, we want to come up with a regression equation. Again, this is not done by hand. However, I'm reminding you, by hand, we came up with n equals 4, r equals negative 0.135 summation of x, summation of y, and all of the above. Now, here's the formulas that we need. And I put both formulas because depending on the technology or text, they might write y hat is b sub 0 plus b1x, or y hat equals a plus bx. And I hope you remember it really comes from algebra of y equals mx plus b. This was the slope. You remember that? And this was the y-intercept. That's absolutely the same concept. This is a line, okay? This is the slope-intercept format, okay? And so in this case, A, in this case, B sub 0 is the y-intercept. In this case, B, in this case, B1, depending on how you write it, is the slope, okay? And so the technology, at least a TI calculator uses A plus BX, okay? So I want you to know that, okay? And so the way they have it, this is the y-intercept, A, and B is the slope. So as far as doing it by hand, uh, if, for example, use this one or that one, in this case, B sub 0 and this B sub 0 is the same as A here. Is y bar minus B1 x bar, where y bar is summation of y over n, x bar is summation of x over n. I mean, just these are the good old, average. So having said that, we want to calculate um, uh, B0, but first we have to go with B1, the slope, again by hand. N summation of xy minus summation of x times summation of y over n summation of x squared minus summation of x quantity squared. And we have all of this calculated already. When we calculated R, we had to calculate all of those. So because of that, it's actually easy to do it by hand. It's been already done, mostly. So we put the formula here. B1 is n, which is 4, times summation of x, y, which is 4d8, minus summation of x10 times summation of y20 over n4, summation of x squared is 36, minus summation of x, quantity squared. You put it into a calculator, you come up with this answer. So because all of this, again, because all of this have been already done, this is a very easy process, everybody. Now, I want to calculate B sub 0. B sub 0 is y bar minus B1 x bar. So I need to calculate x bar and y bar, and each one is divided by n. So you want to divide this one by n for x bar. You want to divide this one by n, again, 4, of course. So y bar, 20 divided by 4 is 5. X bar, 10 divided by 4 is 2.5. And now we are going to go with the formula, okay, and say B sub 0 is y bar minus B1 x bar, which makes it 5 minus B1, which is this number, times x bar. Now notice what I write here. For B1, I'm not going to write this. I'm going to write it with a lot more decimal. Remember, I want to do the rounding at the end. That's why. And it becomes 5.455. Okay. And I'm going to erase my work. So according to what we have here, y bar is negative 0.182x plus 5.455. So this was done by hand. And notice they call it a plus bx. Here's A, of course, with a lot more decimal. Okay. And here's B with a lot more decimal, and we stopped at here. The one next to it is 8, we go to 2. So negative, and pay attention to the sign. So this has been done for us, but I'm showing you because we did the R and we had to come up with all of those, we calculated by hand also. Find the best predicted value of y when x is equal to 2. So here's the general idea. We found that there is no significant linear correlation. Therefore, the best predicted y value is y bar. If there is a correlation, a significant linear correlation, you plug in 2 into this formula. But since we found there is none, then, and the reason was R was negative 0.135, right? So we use y bar. Y bar is calculated to be 5. So that would be the best predicted y value when x is 2. So this happens when there's no correlation. But we look at the case where there is a correlation. And again, I remind you that this was calculated as the p-value that showed way larger than alpha, therefore don't reject H0, therefore no linear correlation. I'm reminding you of what we did and the idea of correlation, and if there is none, then you use the Y bar. A researcher is studying the effects of testosterone injection on different lab mice. She controls the concentration of testosterone injected into the mice and measures their metabolic rates. Analyze the following data set. Will you be running a correlation or regression? Find the value of linear correlation coefficient R and test the claim that there is a linear correlation between the two variables X and Y. And as always, alpha is 0.05 when it comes to science mostly, unless otherwise mentioned. Okay, everybody? In any event, so the first question is, what are we using? We're using regression. Since she controls, and that's the key, the concentration of testosterone injected into the mice and measures their metabolic rates. We are controlling, we want to see the effect, and that is the causation. Otherwise, there is no, there may not be any cause. And so H0 rho is 0, HA or H1. I'm going to use HA here on purpose because sometimes we use H1, sometimes we use H sub A, depending on the text. Rho is not equal to 0, which is always two-tailed test, and that means there's no correlation. Now, what do we mean there is no correlation or there is a correlation? There is no correlation in the first case between the concentration of testosterone in mice and their metabolic rates. In the second case, there is a correlation between the two, which makes it a claim. That's what we are checking. So what happens is that we run this. Okay, this is in L1, this is in L2 if we are using TI, if you are using anything else. And we want to come up with the data and then do the analysis. Definitely, you don't have to do this by hand. So we run it through Excel. Excel gives us R squared, and then these values, which I'm going to discuss exactly what they are. So this is the table. Again, I wanted you to be familiar with that. I think we've seen TI. So what happens if you run it through Excel and it comes up with those values? What do each mean? Okay, intercept, testosterone, coefficient, standard error, t-stat, and p-value, and so forth. So let's look at them. So we are going to look at the same question we've already done part 1. And so then, and as I mentioned, this is the table that we have from the previous page when we run the Excel. Of course, n was 17. There were 17 pieces of data, 17 pairs. Okay. And now the next thing is to do the test statistic. And I'm going to do this again, two methods. One of them is using the formula T equals R minus mu sub R square root of 1 minus R squared over n minus 2. Okay. And we don't have to do any calculation. It's done for us. This number, everybody, is 33.635. It's done for you. You just have to recognize it. Now, again, because things have been done, the next one, instead of the traditional method, we go with the p-value method. So based on the t-test, the p-value, okay, remember, the p-value takes the value of t statistic, which is this number here, and the area to the right, times 2, y times 2. Because it's a two-tailed test. So again, why are we using the p-value? It's given here. I'm going to show you in a moment. That's the reason we are using the p-value. What is the p-value? This by no means is to scale. It's way into the right side. So you locate the test statistic of 33.635, area to the right of it, y times 2 because it's a two-tailed test. And what is that equal to? It's given to us. Look at this number. 1.5316 times 10 to the power of minus 15. Let me tell you what it means. This decimal, move it to the left. How many places? 15. So that means practically 0. Okay. So the p-value is way less than the choice of alpha of 0.05. Reject H0. Okay. And here's method 2. R is 0.9934 from Excel. Any 17 alpha is 0.05 from the Pearson correlation table. R is plus minus 0.456. If you draw a line, it goes really from -1 to 1. But we are interested in these 2 points, negative 0.456 and positive 0.456. This R is way into the rejection region. So in both cases, whether we go with the t-test or Pearson correlation table, same result, reject H0. Reject H0, that's the p-value, which is extremely small. So reject H0 since p-value is 1.5316 times 10 to the power minus 15 less than alpha equals 0.05. So when we are rejecting H0, that means we are accepting HA, H sub A or H sub 1, which is the alternative. H sub A stands for alternative. So the claim becomes true. And then we write, there is a significant linear correlation between the two variables, namely the concentration of the testosterone and the metabolic rate. So therefore, we conclude that there is a significant correlation between the concentration of testosterone in mice and their metabolic rates. Since this is a regression study, the significant slope suggests that the increase in concentration of testosterone in mice causes increase in their metabolic rates. Take a look at this significant slope, significant slope. Look at this one, 199.05934. This is the slope, everybody. As far as, in other words, y equals 199.05934x plus 379.4928. That's the formula for that in essence. We're going to continue with that. Same question, part B, find the regression equation. Well, again, these are the formulas, but let's use the technology that has given us the answer. Like I said, that gives us the following. Y bar is 199.05934 x, or you can stop at 9, plus 379.42 0.492 changes to 3. If you go with 3 decimals, again, however many decimals they ask. And so having said that, we can answer the next part. Find the best predicted value of Y, metabolic rates, when X is equal to 1.3, the concentration of testosterone. We showed there is a significant correlation, remember? Since there is a significant correlation, you must plug in. That means replace the X with 1.3, and the answer is 638.2697. So again, why do we do that? Because there is a significant linear correlation. Using the above pairs and the value of R, what proportion of the variation in metabolic rates can be explained by the variation in the concentration of testosterone? Okay. It can be explained by R squared. So what are we talking about? This is called the coefficient of determination. The proportion of the variation in Y that can be explained by the variation in X is given by R squared. And R squared, they don't have to give you R squared. They have given you R, just square it. And when you square it, you get 0.9869, or simply 98.69% can be explained. The variation, okay, in Y can be explained by 98.69% by the concentration of testosterone. Just a tad, a little bit can't be. It's by other variables.